So we're going to leave fractions behind now, and for the next class, we're going to talk about this idea of a new function that we haven't talked about before, and that is radicals and how they are tied into this idea of rational exponents. So we're going to save these two for a little bit later, but we're really going to focus on this bit of what are radicals and how are they the same thing as rational exponents. Well, let's get you through some language first. You may have seen radicals before, that they have this general format over here. And there's a bunch of different parts of a radical. So first of all, this guy is what we call the radical symbol. The number on the inside of the radical, we call that the radicand. Just put the radicand over here. The number that's on the outside of the radical, sometimes we'll see a 4, sometimes we'll see a 3. If you don't see a number on the outside of the radical, it's always assumed to be a 2. This guy is what we call the index. So the two kind of most important terms here that we're dealing with are the index, which looks like almost an exponent on the outside of the radical, and the radicand, which is the number on the inside of the radical. So we have the index and the radicand. Now the index, there will always be a number there, and if there is no number there, it's assumed to be a 2. All right, so let's take you through what it means for a number to be a square root. So the square root of x equals a means that a squared is equal to x. One more time. The square root of x equals a. So let's take a look at an example. The square root of 25 is equal to a. Well, this means a squared is equal to 25. Remember we talked about before, if there is no number on the outside, it's assumed to be a 2. So the question that you want to say to yourself here is, what number, when you square it, will give you 25? And I hope you can see that that number is 5. Now, the idea is this, sorry, this should read for all a is greater than or equal to 0. When we talk about the square root of 25 is equal to, the square root of 25 is equal to 5, so we know the square root of 25 is equal to 5. The reason we know the square root of 25 is equal to 5 is because 5 squared is equal to 25. However, I want you to keep in mind that there are other numbers when we square them that will give us 25. What other numbers when we square them give us 25? Remember, we square something, you're multiplying it by itself. Well, it's negative 5, right? Because negative 5 times negative 5 also gives us positive 25. But notice this, that even though both positive 5 and negative 5 work, we're going to restrict our answers to only equal the positive solution. That's what this means when it says for all a is greater than or equal to 0. So even though we have two numbers at work, we have positive 5 and negative 5, we ignore the negative solution and we only consider the positive solutions. This is what we call the principal square root. That even though a negative works, we don't say that it works algebraically, and we restrict it to being just the positive value. Let's take a look at another example. Well, the cube root of x is equal to a, the cube root of x is equal to a, which means that a cubed is equal to x. So let's think about this. The cube root of, let's say, 27 is equal to a. Well, that means we have to figure out what number, when we cube it, will give us 27. So this index here, when we reverse that order, acts like an exponent. And think about it, what number when you cube it gives you 27? Correct, that number is 3. So the cube root of 27 is the same thing as saying 3. Now, we don't have to worry about this idea of restricting it to be either positive or negative. It can be either positive or negative if you have an odd index over here. Anytime you have an even index, that value is always going to be positive. So even index, if we have an index of 2, 4, 6, 8, so on and so forth, that value is always going to be positive. That's why we see over here the fourth root of x equals a means a to the fourth equals x, and that a has to be greater than or equal to 0. So in regards to this, again, if we were to take a look at something like this, let's say the fourth root of 16 is equal to a. Well, we want to figure out what number when we raise it to the fourth power will give us 16. Well, let's think about it. Well, what number, if you multiply it by itself 4 times, will give you 16? 2 times 2 times 2 times 2 gives us 16. Even though, again, -2 would work as well, because -2 times -2 is +4. +4 times -2 is -8. -8 times -2 is 16. However, remember, we ignore the negative values. We only consider what we call the principal square root. But if we have an odd index, the odd index, you really have to pay attention to that, because if the radicand is negative, the answer will be negative. If the radicand is positive, the answer will be positive. So what am I talking about? Well, let's practice. Let's take a look at a handful of examples for this over here. Here we go. A, B, C, D, E, F, G. Let me bring these guys back over here. Let's see if we can, all right, here we go. Let's take a look first of all at the square root of 9. Other ones? Oh, we're gonna start. Let's take a look at the square root of 9. Well, when we talk about the square root of 9, we want to know, or the question we're asking ourselves is, what number when we square it? So what number when we square it gives us 9? And I hope you can see that that number is 3. You know, remember what we said before, that even though -3 works as well, we ignore the negative solution anytime our index is even. And here our index is 2. Right? So it's even. If there is no index, it's assumed to be a 2. Okay, let's take a look at B. The cube root of -8. Well, we want to know what number, when we cube it, gives us -8. Think about what number, when you multiply it by itself 3 times, gives you -8. And that number is -2. -2 times -2 is 4. 4 times -2 gives us -8. So that answer is -2. Let's see if I can do this. Sorry. For part C, the square root of 100. Well, again, little square root, little 2 over here. So we want to figure out what number, when we square it, will give us 100. And that number is 10, right? 10 times 10 gives us 100. Even though -10 works, we ignore it because it's an even index. Let's try this next example. The 5th root of 32. Well, the equation we need to solve to figure that out is, what number, when we raise it to the 5th power, will give us 32? Well, let's think about it. 1 times 1 times 1 times 1, that's too small. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So the answer to this one is 2. Okay, let's take a look at the next example, the square root of -25. Again, a little hidden 2 here, even if you don't see it. So we want to figure out what number, when we square it, gives us -25. What number, if you multiply it by itself, that will give you -25? Well, let's think about 5. 5 times 5 is +25, so that's not going to work. What about -5? Well, -5 times -5, that's +25, so that's not going to work. And it turns out you can't take the square root of -25 in the set of real numbers, in the set that we've been simplifying. So the square root of -25 is not equal to anything. It doesn't exist in the set of real numbers. Now, it's going to exist soon, and that is when we start defining a new set of numbers that we call the set of complex numbers. But for now, there is no number times itself that's equal to -25. Well, you can say, well, what about 5 and -5? Well, 5 and -5 are two different numbers. Remember, if you're squaring a number, it has to be exactly the same number. Okay, a few more examples here. The 4th root of 625. Well, what number, I'm going to stop using A, let's use some other letters here. What number, when we raise it to the 4th power, gives us 625? So here's how you handle these if you don't have them easily in your head. You either get your hands on a calculator and you just multiply that number by itself 4 times, or in your head you do this. Well, let me try 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 2 is too small. Let me move up to 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. Still too small, but I'm getting closer. Let me try 4. And then you keep going until you find a number that works. You should get a nice number that works here. And so think about it. What number, when we raise it to the 4th power, will give us 625? And that number is 5. 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. So the 4th root of 625 is the same thing as saying 5. take a minute, see if you can do these last two examples. So just pause the video right here, see what you can do about the cube root of the cube root of 1 over 27, and then the fifth root of 100,000. Okay, so for the cube root of 127, 1 over 27, we want to figure out what number when you cube it, so I'll write it like this, y cubed is equal to 1 over 27. Well, let's think about that. First of all, it has to be a fraction because you're multiplying it by itself 3 times. So what times what times what would give us 1 over 27? Well, the numerator has to be a 1, right? Because 1 times 1 times 1 is going to give us 1. Now think about what the denominator has to be. What times what gives us 27? And that is 3. So 1/3 to the third power gives us 1 over 27. So the answer to G is 1/3. For the last one, take a look at the fifth root of 100,000. Let's call this n to the fifth power is equal to 100,000. Think about what number when you raise it to the fifth power gives us 100,000. And that number is 10. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. 10,000 times 10 is 100,000. So 5 factors of 10 will give us 100,000. So the answer to that one is 10. Okay, let's take a look now at some examples, but we're going to start throwing some variables into the mix as well. So take a look at these examples, and it says simplify the following expressions completely. And we're going to assume here that all of the variables represent positive values. So our variables are not going to be negative. Because if they were negative, we could run into some issues with the fact that, remember we talked about before, if you take an even index of it, some wonky stuff happens, like the square root of -25, we couldn't do that. So we're going to assume that all variables represent positive values, and that's just, you don't have to worry about that. That is going to do absolutely nothing to affect you. We just have to put that there to save our butts mathematically. All right, let's get a good old nice color over here. Here we go. Okay, so the square root of 81x to the fourth. So here's what we're doing. Now there is a property in rational expressions that says the following. That says the square root, or the nth root, it doesn't matter what it is as long as it's the same. The nth root of xy is the same thing as saying the nth root of x times the nth root of y. So what that allows us to do is it allows us to break up products under the radical, assuming that the index is the same. So take a look over here, there's a little hidden too. So the square root of 81 to the fourth power is the same thing as saying the square root of 81 times the square root of x to the fourth. So let's simplify this piece by piece. It just makes it easier for us to, like in little manageable chunks that we can chew. So the square root of 81. Well, you want to think to yourself, what number when you square it, a little hint too over here, what number when you square it gives you 81? And that number is 9. So we have a coefficient of 9 here. For the square root of x to the fourth, same thing. You want to think to yourself, what number when you square it will give you x to the fourth? So what number when you square it? So that is what number when you multiply it by itself will give you x to the fourth. Okay, so remember when the base is the same and we're multiplying, we add exponents. So that guy has to be a 2. X squared times x squared is x to the fourth. So the square root of 81 x to the fourth is equivalent to saying 9x squared. A few more examples, and then there's a shortcut that we'll talk about. But I'm going to see if you guys can figure out what the shortcut is. Ready? The square root of 121 a to the 10th b squared. Well, that is the same thing as saying, we're going to break this apart into 3 chunks. The square root of 121 times the square root of a to the 10th times the square root of b squared, right? We have 3 terms in the factor here. We're going to write these guys as 3 terms in the factor. Now let's take a look at each one of these terms. So let's figure out what the square root of 121 is. Well, what number when we square it gives us 121? That is 11. 11 times 11 is 121. Or what number when we multiply it by itself gives us 121, and that's 11. Let's talk about the square root of a to the 10th. Well, what number when you square it, what number if you multiply it by itself gives us a to the 10th? Remember, when the base is the same and you're multiplying, you add exponents, so that bit is equivalent to saying a to the 5th. And for this last term, for b squared, what number when you square it gives you b squared? It looks like this, and that value is just b, or b to the first, however you want to call it. So this is the square root of 121 a to the 10th b squared. But like I said before, there's a little bit of a shortcut here. I'm going to make sure that you guys are comfortable with a little bit of a shortcut. Now, for the coefficients, we're just going to use that property that I just talked about, the square root and squaring something. But anytime you have a base and an exponent underneath the radical, you can use the index to help you figure out what it's going to be. So for example, I'm just going to put the 2 in here. We know there was a little hidden 2, but I'm going to put it in here so you can see what happens. Think about how you can use a 2 and a 10 to give you a 5. Think about how you can use a 2 and a 2 to give you a 1. If you can see it, the square root of a to the 10th is a to the 5th because 10 divided by 2 is 5. The square root of b squared is equal to b to the first because 2 divided by 2 is 1. That will work. So that is, you can always just take the exponent and divide it by the index, and we're going to talk about why in a few minutes, and that will tell you, this again, this only works for variables, but that will tell you what the exponent will be on your variable when you reduce it. So let's try 2 more of those. Let's take a look at the cube root of 64 times the cube root of m to 15 times the cube root of n to the 9th. I'm going to use a shortcut here too to make sure you can see it. Let's start off with the cube root of 64. Well, what number when you raise it to the 3rd power gives you 64? That number is 4. 4 times 4 times 4 gives you 64. For the cube root of n to the 15th, you say to yourself, how many times does 3 go into 15? Or what is 15 divided by 3? And that is 5. For the cube root of n to the 9th, you say to yourself, how many times does 3 go into 9? Or what is 9 divided by 3? And that is 3. So this guy simplified completely is 4m to the 5th n cubed. Take a look at D and see what you can do with D. I'm going to pause it for a second and see if you guys can do D. Okay, so for the 4th root of n to the 20th, n to the 12th, we can rewrite it like this. We can say this is the same thing as the 4th root of 16, sorry, for the 4th root of 16, m to the 20th times n to the 12th, times the 4th root of m to the 20th, times the 4th root of n to the 12th. Now, the idea is for each one of these, let's simplify them. So for the 4th root of 16, we want to think about what number, when we raise it to the 4th power, gives us 16. So what times what times what times what number, if you multiply it by itself 4 times, gives you 16, and that number is 2. For the 4th root of m to the 20th, 4 goes into 25 times, so we can rewrite that bit as m to the 5th power, or 20 divided by 4 is 5. For the 4th root of n to the 12th, that's the same thing as saying 12 divided by 4, which is 3. So the 4th root of 16 m to the 20th n to the 12th is equivalent to saying 2m to the 5th n cubed. Now, as I was saying before, rational exponents are radicals. So remember, rational exponents, fractional exponents. Anytime you see an exponent that's a fraction, that means it's equivalent to radical form. So rational exponents and radicals are the same thing. One is just written as a fractional exponent and the other is written as a radical. So let's use this definition. Anytime we have something that's in this form, a to the n m over n power, that's the same thing as saying, well, a, which is the base in exponential form, becomes the radicand in radical form. M, the number in the numerator, becomes the exponent of the radicand. N, the number in the denominator, becomes the index. So if you remember it in this form, base to the exponent divided by index form, this is exactly equivalent to writing it in radical form. So what we're going to do with this next handful of examples is make sure that you're comfortable switching back and forth from rational exponent into radical form. Let's take a look at these guys. Let's try 8 to the 1/3 power. Well, 8 to the 1/3 power. 8 is our radicand. 1 is our exponent. Remember, it's going to be base or radicand. Exponent divided by index. Sorry, I should really call it, no, it's okay, I'm just gonna call it that way. And then the 3 in the denominator, that's equivalent to saying the index. If you just remember, it's going to be exponent divided by index. So what this is the same thing as saying, if you think about the cube root of 8 to the first power, well, 8 to the first power is 8. So this is equivalent to saying, what is the cube root of 8? And we know the cube root of 8 is 2. So 8 to the 1/3 power is the same thing as saying 2. Let's take a look at the next example, 16 to the 1/2 power. Well, 16 is our base. It now becomes the radicand. Exponent divided by index, we have an exponent of 1. We have an index of 2. So this is the same thing as saying the square root of 16 to the first power, which is 16. Well, let's think about the square root of 16. Think about what number, when you multiply it by itself, gives you 16. What times what gives us 16? And that is 4. So 16 to the 1/2 power is the same thing as saying 4. Okay, next example, let's change our pen color. Okay. Let's take a look at negative 125 to the 1/3 power. So this is equivalent to saying cube root of negative 125 to the first power. Remember, it's always going to be exponent divided by index. So exponent, index. Well, anything to the first power is that thing itself, so this becomes negative 125. And now we need to think about what number, if we multiply it by itself 3 times, gives us negative 125. Well, first of all, I hope you can tell that it has to be negative, because a negative times a negative times a negative is a negative. And well, again, we start with 3. 3 times 3 times 3, or negative 3 times negative 3 times negative 3 would be negative 27, so that's too small. And then you go up to negative 4. Negative 4 times negative 4 times negative 4 is negative 64. That's too small. And then you try negative 5. Negative 5 times negative 5 is 25. 25 times negative 5 is negative 125. So negative 125 raised to the 1/3 power is the same thing as saying negative 5. Okay, let's take a look at D, and then I'm going to ask that you guys try E on your own. Let's take a look at D. We have 27 to the 2/3 power. Base becomes the radicand. Exponent divided by index. Exponent, index. So this is the same thing as saying the cube root of 27 to the 2nd power. Now, there's 2 different ways that we can do this in terms of simplifying it. That is, you could use the exponent first and then use the index. But the exponent, if you take a look at that, 27 to the 2nd power, 27 times 27 is 729. That's a pretty big number to figure out the cube root of. So what you can do is you could do the index first and then do the exponent. So what I mean by that is the following. We could do this bit first. We know the cube root of 27. That is the same thing as saying 3, because 3 times 3 times 3 gives us 27. And then we can square that, and 3 squared is equal to 9. Now the other way works as well. So that is, if we were to figure out the cube root of 27 squared, that's the same thing as saying the cube root of 729. And the cube root of 729 is 9. So 9 times 9 times 9 is 729. It's just easier to make the number smaller by using the index first, and then make it bigger by using the exponent second. Okay, let's see, we have 3 more examples of this type. Let's try 32 to the 3/5 power. 32 is our index, 32 is our radicand. 3 is our exponent. 5 is our index. So now, I mean, if I'm checking on my calculator, if we do 32 to the 3rd power, we get 32,768. And figuring out the 5th root of that's going to be a giant pain in the butt. So I'm going to use the index first to make it smaller, and then I'm going to use the exponent to make it bigger. The 5th root of 32. What number, when you raise it to the 5th power, gives you 32? 2 times 2 times 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, so that's 2. Now we're going to use the exponent, which is a 3. We know 2 to the third power is 8. Okay, let's take a look at 2 more examples. Let's take a look at F, and then we'll take a look at G. Negative exponent. Remember, now we're going to deal with the fact that we have a negative exponent. And anytime you have a negative exponent, I want you to do what? Cross the what? Change the what? Cross the line. Change the exponent sign. So this is the same thing as saying 1 over 625 to the 5/4 power. Well, what does that mean? That's the same thing as saying this, 1 over the 4th root of 625 to the 5th power. You gotta try, I think if I try 625 to the 5th power, my calculator, yeah, it's a massive number. My calculator can't even handle it. So what I'm gonna do first is take the 4th root of that number and then raise it to the 5th power. So the 4th root of 625, or what number when we raise it to the 4th power gives us 625? That number is 5. And then when we take 5 and raise that to the 5th power, let's do 5 to the 5th power, we get 3,125. So the answer to that one, simplified completely, is 1 over 3,125. And you need the 1 over because the exponent's negative. Okay, let's take a look at G. We have 8 over 81, excuse me, 4 over 81 raised to negative 1/2 power. So I want you guys just to see this, that if I put a little exponent of a 1 there, I put a little exponent of a 1 there, then we have a base of 4, we have a base of 81. So 1 times negative 1/2 is negative 1/2. 1 times negative 1/2 is negative 1/2, right? So when you distribute the exponent in, now to make each of these exponents positive, we're going to cross a line and change the sign. So 4 to the negative 1/2 becomes 4 to the 1/2 in the denominator. 81 to the negative 1/2 becomes 81 to the positive 1/2 in the numerator. This is the same thing as saying 81 to the 1/2, remember exponent of 1, index of 2, you don't have to write the 2 there. Same thing with 4 to the 1/2, we have a base of 4, exponent of 1, index of 2. The square root of 81 is 9, and the square root of 4 is 2. So we end up with 9/2. Okay, let's finish with a few examples now. Again, what I wanted you to be familiar with is how we can rewrite rational exponential form into radical form, and then how we can evaluate them. And also what it means to simplify some radical expressions. And we're going to take a look more at simplifying radical expressions. But the last thing that we want to do is go back and look at the properties of exponent that we talked about. So let's take a look at a few of these expressions. And so these are the properties of exponents we talked back about the first day of class. We're going to go back and review them, but we're now going to introduce them with fractional exponents. So all the properties are the same. What makes this just a little bit different, just a little bit more interesting, just a little bit more complicated is the fact that the exponents are going to be fractions. So let's take a look at the first example. This is x to the 3/4 times x to the 2/5. Well, you remember when the base is the same and we're multiplying, which we're doing here, then we add exponents. So we need to figure out what 3/4 plus 2/5 is. Because if we know what 3/4 plus 2/5 is, that's going to become our new exponent on our x because the base is the same and it stays the same. All right, so what do we remember about combining fractions? Well, first thing, you need a least common denominator, and the LCD of 4 and 5 is 20. Once you have 20 as your LCD, you then have to write equivalent fractions using your new LCD. So to get from 4 to 20, you multiply by 5, and 3 times 5 is 15. To get from 5 to 20, you multiply by 4, and 2 times 4 is 8. So we end up with 15 over 20 plus 8 over 20, and that is the same thing as saying 23 over 20, right? The denominator stays the same. When you combine numerators, you get 23 over 20. So again, it just makes it more interesting because instead of dealing with exponents that are integer values, we're now dealing with exponents that are fractions. Fractions make everything a little bit more interesting. All right, let's take a look at the next example. M cubed times n to the 1/2 raised to the negative third power. Oh, my pen's going crazy. Oh, there's a little bit better. M cubed times n to the 1/2 raised to the negative third power. So for this example, remember what happens when you raise something to a power and you raise it to a power again. So if we had something like this, a to the 4th raised to the 5th power. Well, if that's the case, then we multiply exponents. That's the same thing as saying a to the 20th. It's the same exact thing here. So we're gonna multiply exponents just as some of the exponents happen to be fractions. So 3 times negative 3 is negative 9. 1/2 times negative 3 over 1 is negative 3 over 2. Okay, now in our denominator, we have m to the negative 2nd, n to the 5/7 squared. So we're going to do the same thing. The bases stay the same. Let's multiply exponents. Negative 2 times 2 is negative 4. 5/7 times 2 over 1. Remember, multiply numerators, multiply denominators, and we get n to the 10/7. Okay. Once we get to this point, now anytime I have a fraction that's negative, I'm going to cross the line and change the sign. And positive fractions, we're going to leave them alone. See m to the negative 9th? That's going on down. It becomes positive. See n to the negative 3/2? That's going on down. It becomes positive. It's so excited. Look at it. And my pen's just like shaking with joy over here. See m to the negative 4th? Now that negative exponent's in the denominator. It's going to come up. Cross the line, change the sign. N to the 10/7, it's already positive. We're just going to keep it in the denominator over here. Okay, I have to finish this before my pen completely dies on me. So let's see what we're left with. I want you guys to picture this. M to the 4th divided by m to the 9th. We have 4 factors of m on top. We have 9 factors of m in the denominator. If you cancel out those 4 factors that are the same, we're going to be left with m to the 5th. Take a look at n to the 3/2 times n to the 10/7. Right, the base is the same. We're multiplying, so we're gonna add exponents. So we need to figure out what 3/2 plus 10/7 is. So 3/2 plus 10/7. Well, let's do this first. We have an LCD of 14. To get from 7/14 multiplied by 2, 10 times 2 is 20. To get from 2 to 14 multiplied by 7, 3 times 7 is 21. So 21 over 14 plus 20 over 14, that's going to leave us with 41 over 14. And notice that we're not left with any terms in the numerator. If that happens, just put a 1 there to represent that. Because what you're really doing here when you see m to the 4th divided by m to the 9th is you're canceling out those factors of m, and m divided by m, any number divided by itself is 1. So this is the answer to B. Let's finish here with C. Questions like C always like to show up on final exams. You guys catching my hint? So this is a good question to ask for this example. We have 4x to the 1/3 y squared raised to the 3/2 power. First of all, notice my 4 doesn't have an exponent, so I'm going to put a 1 there. 4x y. No? Here, right? Once you rewrite your bases, when you raise something to a power and you raise it to a power again, you multiply exponents. So let's do this. Y squared raised to the 3/2 power. I'm going to call this 2 over 1. Well, 2 times 3 is 6. 1 times 2 is 2. So we get y to the 6/2. Let's take a look at x. 1 times 3 is 3. 3 times 2 is 6. 1 times 3/2 is 3/2. So, okay, let's reduce or simplify anything we can. Well, y to the 6/2 power, 6 divided by 2 is 3. X to the 3/6 power, well, 3/6 is a proper fraction. It reduces to 1/2. And for 4 to the 3/2 power, remember that anytime you have a rational exponent, you can rewrite it in radical form. So in radical form, it's the same thing as saying, oh, see, my pen's about to die. It's going crazy. 4 is our radicand. 3 is our exponent. 2 is our index. Okay, so the square root of 4 is 2, and 2 cubed is 8. Remember, so you do this first. The square root of 4 is 2, and 2 to the third power is 8. Or you can see the square root of 4 cubed, 4 times 4 times 4 is 64, and you know the square root of 64 is 8. So that would be this guy simplified completely. Okay, so we finished talking about the relationship between radicals and rational exponents. We finished talking about how you can convert back and forth from radical form into rational exponential form. We did some examples simplifying them. And then we talked about properties of exponents when the exponents are fractions. And we noticed they're just the same as when the exponents aren't fractions. It just makes it a little more difficult to operate on because we're dealing with fractions. Now it's that special time of day for you to do your homework.